In this video, we're going to talk about the cross product, which is also called the vector product. If you're given two non-zero vectors in R2, it's not necessarily possible to find a vector perpendicular to both of the given vectors. For instance, in the example shown on the right, if we determine a vector perpendicular to one of them, it won't be perpendicular to the other, and vice versa. There's no one vector perpendicular to both of the given vectors there, because we only have two dimensions to work with. So as we can see, given two non-zero vectors in R2, it's not always possible to determine a vector perpendicular to both of them. However, it's a different story in R3. If you're given any two non-zero vectors in R3, it's possible to find a third vector perpendicular to both of the given vectors, and one way of doing that is called the cross product. The reason that it's always possible in R3, if you have two non-zero non-collinear vectors, is because you have a third dimension. Think of the perpendicular vector as coming out of the page or going into the page. Perhaps it's helpful to think of the x and y and z axes. The third dimension provides us with an opportunity to find a vector perpendicular to each of the given vectors. So suppose that a is equal to a1, a2, a3, and b is equal to b1, b2, b3. If we let v equal a2, b3 minus a3, b2, comma a3b1 minus a1b3, comma a1b2 minus a2b1, then we can say that v is the cross product of a and b, and we can write this as v equals a cross b. And so we can say that a cross b is equal to that expression that I stated earlier. Now, if you want to show that v is perpendicular to both a and b, it's actually a pretty simple process. Just determine the dot product of a with that vector that we called a dot b. If you do that, you'll get a1 times a2b3 minus a3b2 plus a2 times a3b1 minus a1b3 plus a3 times a1b2 minus a2b1. Then we can distribute a1 into the first bracket, distribute a2 into the second bracket, and distribute a3 into the third bracket. Now when we do that, we get a positive a1, a2, b3 term and a negative a1, a2, b3 term. We get a negative a1, a3, b2 and a positive a1, a3, b2 and a positive a2, a3, b1 and a negative a2, a3, b1. They all cancel each other out, and the answer is 0. So that vector that we determine with that formula dotted with a gives us 0, so it's perpendicular to a. It's also perpendicular to b for the same reason. b1 times a2 b3 minus a3 b2 plus b2 times a3 b1 minus a1 b3 plus b3 times a1 b2 minus a2 b1 is given here. We can distribute b1 in, and we can distribute b2 in, and we can distribute b3 in. And if we do that, we get a2 b1 b3 and also a negative a2 b1 b3. We get negative a3 b1 b2 and positive a3 b1 b2, and we get negative a1 b2 b3 and positive a1 b2 b3. Everything cancels out. We get 0. So that same vector is perpendicular to both a and b. And so a cross b is perpendicular to both of them. Now, there's a slide that we'll go through in a different video where we develop a formula for a cross b. But before we get into that, that'll be in a different video. Let's talk about a process for determining a cross b, because most people don't actually memorize the formula for each time they go through it. So what we're going to do instead is make two columns. The first column has the y coordinate of a, then the z coordinate of a, then the x coordinate of a, then the y coordinate of a. And the second column will have the y coordinate of b, z coordinate of b, x coordinate of b, and y coordinate of b. And actually, technically, we should be saying component, not coordinate for each of those, because we're talking about vectors. But then what we're going to do is evaluate three sets of down minus up. So suppose we were given these two vectors, -1, 3, 2, and 2, -5, 6. What we can do is in one column write 3, 2, -1, 3, just like this. And in the other column write -5, 6, 2, -5, like this. Now some people prefer to write them as rows, and that's, it's going to work the exact same way. They're going to get the same answer that we get. Sometimes I use columns, sometimes I use rows. It doesn't really matter. But what we then do is we say, okay, what's 3 times 6 minus 2 times -5? And we come up with an answer. What's 2 times 2 minus -1 times 6? We come up with an answer. And what's -1 times -5 minus 3 times 2? And we come up with an answer. Okay? And when we do that, we get 28 for our first answer, 10 for our second answer, and -1 for our third answer. What that tells me is that P cross Q will equal the vector 28, 10, -1. And you might be wondering, well, what's so significant about that? What's significant about that vector is it's perpendicular to each of the two given vectors. Okay, so -1, 3, 2 cross 2, -5, 6 equals 28, 10, -1. If we take the first vector and dot it with that vector, we get 0. And if we take the second vector and dot it with that vector, we get 0. But what if we want Q cross P? Well, then in that case, we'll just switch the columns. Left becomes right, right becomes left. And again, we'll do down minus up. And when we do that, we get -28, -10, +1. And you might recognize that that's just exactly the opposite vector of P cross Q. But it's also perpendicular to each of the two given vectors because the dot products equal 0. So we can say that P cross Q will be equal to -Q cross P and vice versa. But most significantly, in both cases, the dot product of that vector that we get with each of the two vectors given will equal 0. It'll be perpendicular to both of them.